Boom.
No.
Well, let me tell you a story about these atoms was made. No, I'm just kidding. Monaco?
No.
No.
Yeah.
I
The
love
evolution.
the evolution of the atomic model because it connects to history. Okay?
Yeah. This is your jam. You like
From
this stuff.
Democritus to Niels Bohr, model of the atom changed over time. So there's your learning target.
Yep.
Explain how the model has evolved and relate evidence to models of the atom.
There we go.
Okay?
First dude, Democritus. Old.
Sweet, dude.
Yeah, like we couldn't even take a picture of him. He's so old. We had to make a statue.
Toga.
Yeah, seriously.
Toga.
So he came up with this word atomos, which is Greek for
Mhm.
cannot be broken down.
Yeah.
And this idea of the smallest unit of matter was really good. What he actually thought of way, way back in the day, if I remember correctly, was an apple.
Yeah, apple
you
or grape
slice
or
an apple
cheese
in
or
half,
something, right?
You got a half an apple, and then you slice the other half. And he said he was theorizing, well, what happens when I get to the point where I can't break it in half anymore?
Isn't there a smallest piece of that thing that remains that thing?
And this novel idea turned out to be, is it a truth?
Some truth, yeah, for sure. And then fast forward, about 2,500 years almost.
Yeah.
Like,
Long time.
nothing happened until the 1850s when John Dalton showed up. And
5 huge postulates. Sorry.
5 big ideas, but he still had no actual physical evidential proof yet. His ideas were as follows. Arytans made of atoms that are very, very small.
Yep.
And atoms of a given element are identical. So gold is gold is gold is gold.
And carbon is carbon is carbon is carbon.
Atoms can't be broken down, created, or destroyed.
Which is what Democritus said. He just expanded.
He expanded on it, and it goes into the whole element can't be broken down by chemical means, right? That's where we get that definition from.
Yep.
Atoms of different elements combine in simple ways, ratios, to form compounds. Again, throwback to the first unit period. Particle models, right?
Right.
2 different color spheres touching, connected. That's a compound. That's a ratio.
But this is
truth.
This is the one for me that has like the most profound effect on the rest of the units for us, because H2O
is
means
H2O.
There's 2 H's and 1 O. There ain't no half of one. There ain't no third of one.
If you take an H away, it's not H2O anymore. It's
There you
something
go.
else. And that was kind of a big deal back in the day. A water is a water is a water is a water.
Right.
In chemical reactions, atoms are combined, separated, or rearranged, but they're not created or destroyed. So this provided a very solid foundation for, realistically, the further study of chemistry. Like, control your experiments. If these things are true, the things you're observing have to have an explanation that relates to the atom. And so in some ways, many think that he's the father, the originator of modern chemistry.
And part of that, like you said, is the father is to
Modern.
this point, we can't dispute any of these 5 things yet. Like, these still are all 100% valid, and we've got much better instrumentation to prove stuff.
It's been
We've
almost
expanded.
200 years.
Right, and we've expanded on all of these things, but
And
not
they're
one of
still
these, not one of these has been disproved.
Right.
So that's, to me, that is pretty wavy.
Big deal, Dalton.
That's pretty wavy.
Leonard, what you know about Thomson?
He had the plum pudding model. So there was just, you got your pudding and you've got some raisins or whatever you want all throughout it. There's stuff in there, but they're in no particular order.
Yeah.
Okay, good way to put it.
Mm-hmm.
Keep going.
Sure, those things would be the electrons, the first subatomic particle.
One of my favorites.
Yes. And those have the negative charge.
Why do they have a negative charge?
Thanks to the cathode ray experiment.
Yes.
Yeah, so do you see these deflection coils? Those had a positive charge. And when he started throwing the beam through and it bent, we know negative is attracted to positive, and that's how he theorized that they had a negative charge to them.
Realistically, originally, he just assigned their value to be negative. He's like, it's opposite whatever the other the deflection coils was, because they're attracting. So I'm going to call it negative.
Right.
That's why electrons are still negatively charged, people.
Right. And guess what? Those cathode rays were in TVs up until, 15 years ago, 10 years ago?
Yeah, those big old TVs you see on the curb, ready for the scrappers.
Yeah.
Cathode rays. Now, Ernst Rutherford, he performed a very famous golden foil experiment where
Can I draw a little bit during this?
Yeah, go ahead. He took an alpha particle beam, which was known to be a positively charged type of beam, and shoot it through a very tiny slit at a gold foil, essentially making like a particle laser, like bah.
Yeah.
And
What happened?
he expected that they'd all travel straight through this piece of aluminum foil, like you're shooting bullets at, a shower curtain. He expected every single one of them to go straight through.
Know what else happened?
But not all of them did. Some bounced back.
So one that went like this said,
nope, I'm going to come
Kapow!
back the other way. This was really, really astonishing to him. And the explanation that he came up with surrounded the fact that there must be a small, dense, positively charged center in the nucleus because something is deflecting these alpha particles, which I know to be positively charged, back right at me. So this was like astonishing at the time.
and what else happened?
The explanation for why many of them went straight through was
What
that
else happened? Here we go. Wait, let me do it. Oh, I'm sorry. Go ahead.
the explanation for why many of them went through was that the atom's actually mostly empty space. So there's a very small dense positive core that occasionally will deflect a positive charge back at the originator.
Okay.
But most of the atom is a whole lot of nada. So the alpha particles would go straight through still. And so his findings were atom has a nucleus that's positively charged.
Yep.
And most of the atom is actually not really anything.
Sure. So the one piece I drew in green that's deflected is the one that comes near the nucleus. Positive and positive repel. So if it was a direct hit, it repelled it. That's where the dense comes in.
Mm-hmm.
And the repel is the positive. That's how he gives
Close
the charge.
interaction. Yeah.
Right. And there's kind of his model.
So yeah, he's got the nucleus and electrons around it, but mostly a whole lot of nothing.
Right. Good.
Two of my favorite subatomic particles.
And then Niels Bohr comes along
Ah.
and he redefined the model to explain why they emit light when they are zapped with energy. Now, this is on simply every Regents exam.
Oh yeah.
So I know we're learning it in, end of September, right? But it's going to be there. So this is how it works. Ready? I give it energy, jumps up an energy level, right? And so this is how we came up with this idea that the orbitals have energy levels of distinct energy. And then when it falls back down to ground state, it gives off, you see the yellow wavies, light. And light is every light we see is a wavelength. Different colors, different wavelengths. Different wavelengths, different energies.
Mm-hmm.
So now we have different energies for every energy level, and that's what Bohr did.
Yeah.
Something like that.
Ooh, wave mechanical,
It's the best one we have right now to explain what's actually happening in there. So it's the most accurate model and takes a lot of complex mathematics, showing that the electrons do not actually go around the atom like a planet would around the sun, but instead they're traveling randomly as long as they're staying in the space, that orbital that they're supposed to be in.
Yeah, that little cloud.
Yeah. And they have weird shapes, cool shapes that determine lots of different things later down the road when you're studying them in
So
college.
there is a quick picture of the evolution.
Yes.
We went from Dalton to Thomson to Rutherford. And then Bohr thought they stayed right in those energy levels. And then we proved with calculus that those energy levels have more of a three-dimensional shape to them than they do a ring.
Yeah, for sure. And the Rutherford model is the ubiquitous symbol for atoms. I have a tattoo of that.
Right.
So, like, you see that? Oh, that's an atom. Yeah, well, it's evolved a little bit since then, too.
Right. And so now coming out of this video, that orbitals question is going to be key because we need to know what an orbital is. The
Ground state, excited state. But there's a whole lesson on later on the video. On the
there is?
lecture. Yeah, excited state, ground state. This is just a history of the evolution of the model of the atom.
Right.
Doing too much.
Yeah, I just want to let you know it's important.
It is.
It's important.
That's all, folks. I click the button and it turns it off. Click the button. Turn